the next one is market clearing and mechanisms, and will be presented by Fortiss and Framatome.
I think we have some confusion, but Joseph, then you show the first slides.
I will probably show all slides, Markus. Okay.
Okay.
Because then we don't need to change.
It makes sense. Sorry, I stole your sharing, so you need to reshare.
Oh. I did miss that. Okay. Yeah. Now hopefully it works. And thanks, Jan Stegersman, for this perfect introduction, because you already talked about the cross-commodity markets and...
No, Jan Stegersman, terve.
Sorry?
Mä olin tuossa kiinni pitämässä yhtä esityksestä yhdessä kokouksessa, niin en päässyt puhelimeen, mutta ajattelin, että mä soitan saman tien takaisin.
Okay, for non-Finnish people this is difficult to understand. But I think it's not addressed to us.
Maybe you should mute.
Näin on.
Jan?
Joo, siis se pösö, se 1007, kyllä.
Okay, hopefully Jan will recognize that he is still unmuted. Okay, again, thanks for the introduction, for the perfect introduction.
Selvä. Ei tähän niille jarronisteille nyt mitään, niin, niin tietää ton, niin, niin täytyy sitten vaihtaa jossain vaiheessa ne sylinterit.
Someone with the rights who can mute him.
Niin, ei siinä mitään. Niin, satulat edestä ja sitten sylinterit takaa, joo. Joo, kyllä. Niin, niin.
I think Markus or Satu should.
Okei, no sitten se vaan se jostain saattaa se, mä mietin, että olisiko siinä niin lohkolämmittimen jossain, mutta hyvä, ettei ole mitään moottoria.
Force muting.
Sorry.
Niin, se on ihan jees.
So you see, do you have the rights to mute?
Can you just mute him? He is talking about the car repairment and the brakes.
Mutta niin pääseen siihen aikaan.
Can mute him? It's not relevant to this.
Hyvä. Niin, mitäs sä meinaat, minkäs kokoinen paketti tuli?
Satu or Markus, could you mute? I don't have the rights.
Good.
Yeah, okay, now it's...
maybe it's over.
Okay, yeah, anyway, we will talk about the market clearing and mechanisms. Yeah, let's dig into it. First, Markus will talk about the implementation in the DEcentralized project, which...
Mä tuossa just ennen
Maybe you see call Satu or Markus so that they can mute you.
Hyvä, kiitoksia. Joo, moro.
Jan.
Jan?
No.
You're still unmuted.
I also wrote him a chat message, but he probably doesn't. So
sorry. No, it's
perfect. Good. Yeah,
Thank
please
you.
mute yourself, Jan.
I will mute myself. I'm very sorry. There was a telephone call.
No problem. Thanks.
Okay. Yeah, thanks again for the perfect introduction. As you talked about the cross-commodity markets, Markus and me will now introduce how we implemented those in the DEcent project. First, we will talk about the DEcent standard, which is the local energy market based on merit order. Then I did something to address these linked markets using the gossip algorithm, and later on I will give a short comparison between both approaches. Yes, now it's time for Markus to introduce the blockchain market.
Right, so we heard a lot about blockchain markets. We used the IBM Hyperledger Fabric. Of course, during this project, we also experimented with the Ethereum-based Energy Web Foundation, which is quite popular in the domain. But we chose for that Hyperledger Fabric framework. So we built up a permissioned blockchain, which we implemented. And we had a Hyperledger Explorer instance running, which we put on our public port. sorry, which was available and used to check the current state of the blockchain so that every partner is aware that the system is up and running. Of course, it lacked of stability in the first iterations, but we tried our best to get a stable version up and running. Of course, we also implemented a client application in order that every partner and every partner side could interact with the blockchain and the smart contract in order to post offers and also post demands, whether they want to sell electricity or heat or purchase electricity and heat. And due to the permissioned approach we chose, it was also represented by an authorized peer, and we also provided the client application in order to interact with the blockchain. And of course, not only the clients participated at the market, but also the operator. I think that was also visible in Jan's presentation. I'll have a closer look on that on the next slide, but the market operator was responsible to clear the market and had a dedicated or a specialized role according to the certificate. So if we switch to the next slide, we see the overview of the whole market. So we had a certificate authority in order to authorize dedicated peers or newly peers which appear in the market, that they can execute the commands on the smart contract. Of course, we also had an endorsement policy for every peer in order to promote the offers and demands which were placed on the blockchain, so to say. And so we see within that box, we have the different entities, the different houses and prosumers in our system. Everyone had 2 peers in order to interact with the market and also to do the validation, so building the consensus mechanism. And of course, what we see below the box, we have that market or operator instance, which could also interact with the blockchain in order to do the market clearing. So the offer interface of the smart contract had certain information which was included. So the amount of electricity, how much I want to offer on the market, what is the price I'm willing to sell that amount, also validity period, from and until or the time horizon within which the offer is valid, and also can be provided to another entity who has matching demand. And if we go to the next slide, we see the controller, which is also included in every peer. It operates more or less the offers, and only some operations are, as explained earlier, are available or accessible for dedicated roles based on the certificate that peer brings with it. So every entity was able to create offers, to delete offers, to update offers, of course, only from their own peer, which they set. So you can't delete any other offers from other peers or participants. But of course, you are able to query offers and also to query for organizations which are participating at the market. And only the operator role, according to his certificate, was also able to do the market clearing. And that clearing mechanism was implemented using a merit order principle. So this is quite common in the day-ahead energy markets. And here on the right-handed side, we see more or less how the merit order principle works. So we have 2 ordered lists, and also the ordering was done on the chain, so within the smart contract. So it was an operation. And then we have the supply everyone who provides electricity or heat in an ordered list by price ascending, and the demand the other way around, so with a descending price. And the merit order price is where those two graphs intersect. Of course, we also had several special cases which we evaluated within a paper together with Josef or Framatome or correlation. And also these are implemented correctly, at least according to what we did in the paper. And those two markets we implement, so heat and electricity market, were up and running. The merit order mechanism and the matching operation also allowed for partial matchings. So if only a subset of, or a part of the quantity of the energy offered or requested could be satisfied, this had happened. And we also allowed for linked offers. So for special cases, when I have a heat pump in one house, I can only offer heat if I upfront could purchase electricity from the other market. So also this logic was implemented using the smart contract. We go to the next slide. Here is more or less again that principle of the different organizations. So the clients running at the different partner sites with the two peers within the client, which were able to really post offers or post the demand or delete it or update it. It was shared and distributed by all the authorized parties within the virtual neighborhood network, so to say, and placed on the blockchain, whereas the operator was responsible in the end to do the market clearing. And based on that market clearing, we also got the approval more or less for dedicated orders, which matched with offers or demands from the other clients. And on the last slide, I think from my deck, no, we also did the market evaluation, of course. Therefore, we used our own simulation environment, which was capable, or we implemented 100 simple buildings, which did 10 bits every 15 minutes for each building. And we investigated different consensus mechanisms. So in order to agree if an order is approved or not, or if an offer is valid or not, and if the matching could occur. So proof of work is what mostly everyone know in terms of Bitcoin, so the currency. So every participant is given a very complex task, and the own hardware is used to solve that difficult task in order to validate a block on the chain. And another approach or another consensus mechanism is the proof of stake, where the next participant who is allowed to validate a block on the chain is determined by the means of a weighted random selection, whereas also this is not a fair approach, because those participants who are earlier in that network are weighted a bit more, and therefore the selection is not as random as proposed. And there is also a third consensus mechanism we looked into, the Byzantine fault tolerance, whereas all the registered identities, so all the participants with an available certificate or with a valid certificate, were chosen, as well as a redundant reconciliation for the validation. And in the table on top, we see for the different options, or not really options, but the different aspects. We had a look during our investigation. So node identity management, of course, proof of work, as Bitcoin is an open system, as well as proof of state. Whereas the Byzantine fault-tolerant system is a permissioned blockchain, so to say. So you need to be validated by all the nodes or by the certificate authority, as we used in our Hyperledger approach. Then we, of course, had a look at the energy saving potential, because what we hear often in the public, using blockchain is a waste of resources and a waste of energy. And at least for proof of work and for proof of work, there is no energy saving potential, because you need to use your own hardware to solve these complex tasks. Whereas for the proof of stake, of course, there's a partial potential to save electricity. And within the permissioned approach, as for the Byzantine fault-tolerant consensus mechanism, we see the most energy saving potential. And of course, also due to security reasons, we looked at the tolerated power of adversary. And so computing power, so if you have a sufficient amount of computing power for proof of work, then you can more or less manipulate the blockchain. For proof of stake, it's a bit more difficult to do so. And in the Byzantine fault-tolerant system, a number of 33% faulty replicas is required in order to manipulate the system. When it comes to the computation time, so the complexity, in order to do the market clearing itself, mostly we had the complexity of n log n in order to sort our lists of offers and demands. So also the clearing time increased line arithmetically to the number of bits which were available in the network. So these were our evaluations in short. And on the next slide, now this is my last slide, we see a short video that we really also did some implementation in order to start up the market using Gradle. And here we just see if we run the video. I'm not sure if it works properly. Yeah, so this looks good. So we have those two market clearing services. So the operator role, we have initially those 5 organizations which participated in the project, and also did the clearing periods for 15 and 30 minutes ahead in time, in order to compensate for the longer time until heat is really available. So therefore also the time horizon where the clearing happen is also a bit higher than the usual day ahead market time periods. And what we also saw is the posting of offers, which was tracked and monitored by the market controller. And then I would hand over back to Josef in order to continue with a gossip approach we also had a look into. Or not we, but yes, within the project.
Yeah, exactly. Thanks, Markus, for the presentation. As Markus already said, I also looked into an alternative market or alternative algorithm, which is the gossip approach. And I also wrote some papers about this. In general, for the gossip algorithm, you need a communication network, and the idea is that information is spread all over the network by peer-to-peer information spreading. So as you can see, we have a random gossip approach where one knowing node addresses a randomly chosen neighbor. Then we have a geography network where the hop limit is not limited to one, but a node can always access any other node within the network. And we have the broadcast approach where information spread is done to all surrounding neighbors. For the peer-to-peer consensus, we did not exactly use the information spreading just, but it is more a bilateral or a bidirectional communication. So the local consensus is done as shown here. We request another server, and then in the main calculation happens during steps 8 to 10, where the cost minimum is calculated. So the cost minimum or optimum of the cost functions needs to be found within 2 participants. And to get a better idea, I plotted here some cost functions. For example, a photovoltaic power plant, it does not care how much it puts out, and thus the cost function is just a flat line. Next, we have a battery storage with who can also have negative power outputs. And last but not least, we have a fuel-based generator, which can be represented by maybe a more complex cost function. For example, at low power outputs here, we have bad efficiency, and thus the gradients are higher. And for example, in the low and the high regimes, we have high gradients due to high wearing on the components. And the global consensus compared to the local consensus is the minimum overall cost with a steady overall power output. So within all entities or participants, the power output is given at the beginning of this consensus finding, and then with this peer-to-peer trading or local consensuses, over and over again, we reach then a global consensus by minimizing the cost between 2 peers. So this is the goal that we want to optimize. We implemented, for one paper, we implemented 2 approaches. In general, the OPC-UA solution was reliable and did a good work. Next, I wanted to look into the results from this simulation. As you can see, we have several fixed nodes who are defined, for example, by polynomial coefficients. So these are the cost functions and initial values, for example, and boundaries, so the minimum and maximum power output. We varied the number of participants, and they always, if we ran a scenario with 8 entities, we chose the first 8 entities, so it was comparable. Next, we also differed some other parameters in the scenario. For example, the delay. A server waits for a time duration where it is accessible for other nodes to be addressed for the peer-to-peer consensus. Otherwise, if there was no time delay and everybody would just try to reach out for other nodes, then there would be it would get too crowded and the communication would break. We ran all the simulations for 90 seconds, and we did each scenario 3 times. And here we can see the result for one run. As you can see, we have this all the small lines represent the costs that each entity has, or how they develop with after all the tradings. And the red curve shows that the overall, the sum of the costs decreases, which is the optimization goal, of course. Yes. We have a fast drop in the beginning and an intermediate drop afterwards. But in general, yeah, we wanted to have a comparable behavior with the merit order, and this is what I'm showing right now. The merit order has, okay, we have this gossip approach that I explained before, and to compare it, we need to look into the merit order, how it works, and then we defined that it is comparable. So first we have the bits which are represented by energy and price for one market clearing interval, and we have the sorted queues. So the demand and supply queues that Markus already explained. Then there is a matching price, and of course, the optimization goal is to maximize this integral that I highlighted gray. So the total cost drop should be maximized by the merit order algorithm. And this leads to the comparability. Yeah, we showed that the integral of the bits is exactly the cost function for the gossip. So we approximated some bits from a merit order scenario and saw that the deviations were about 0.5% at maximum. And as you can see, the highest deviations are where the bits are changing. So from 0 to 200 megawatt hours, we have the first bit. Afterwards, we have a new price, and then again a new price. And at these definition edges, we have the highest deviations or errors. So the conclusion, we have the same optimization goal because we can translate one function to the other. So the bits are translatable to the merit to the gossip cost functions. Difference between both approaches is that the merit order needs a central calculation unit, and the gossip approach is a real decentralized approach where we have a real peer-to-peer trading. The merit order market is more efficient because there is this coordination, and we have a fixed algorithm that can be run on one entity, whereas in gossip we also need the communication always. But the gossip, for example, has a better resilience. For example, if in merit order market the market entities breaks, nothing works. But if we look into gossip, if one client breaks, there is no harm on the overall system because all the others still can trade. One other thing that we can do in gossip markets is we can have more complex cost functions. I would just go through this. There is a problem that in merit order we the gradients can only increase. There is no possibility to decrease a gradient over the energy output because the bits will be ordered by the algorithm. So gossip solves this one problem, and then another issue is conditional bidding. If we have two markets that are cleared at the same time in merit order, the conditional bidding is very difficult, and there is, from what I know, no solution that does this just fine. But in gossip algorithm there is, because we have these micro trades between always between two participants. you can define boundaries for your cost functions. That are conditioned to the cost function or to the current set points. So, for example, here we have in the end we have. Yeah, it's difficult to say. I'm very restricted with the time, so I cannot explain this more properly. But as an output, we have that the power outputs were set closer to each other because the deviation is limited from the conditions. Otherwise, this output for heat could have grown to a higher level in merit order. So here the gossip approach also has a small benefit over the merit order market. Yes, I worked on that, but this is not part of this presentation now. And thank you very much for your attention. Let's hand over to the next presenter.